Hello everyone, this is section 16.2, line integrals. And I get a little remark to start off with. It's basically an integral along a curve, and it represents the area of the surface under a function with respect to s along a curve C, where ds is the arc length of the curve. So I know that doesn't really mean that much, so I think a sketch will help. So let's consider a sketch here. And let's say we have a curve, Z of course. Let's say we have some curve C here, down here in the XY plane. So this will be our curve C. And we'll get a function. And you see it starts here, maybe goes up like this. So that's going to be our function, f of xy. So the idea is that we're calculating the area of this piece along that curve. So it's almost like a little curtain, like the area that's contained underneath the graph of the function along that curve, between these two, or x and y values. So theoretically, you take little strips, like let's say, for example, I took two little strips here, and I blew that up, and we basically get the curve down here and our function, and you've got these strips. And I'm not going to go through the theory completely, but this is the idea of the change in s. Okay, so you're thinking of s again as the arc length of the curve, and if we call it maybe s sub k to represent a specific interval, then maybe this will be p sub k. This might be the point before it, so p sub k minus 1, so we're using those as the points on the curve. And then there's this, we might call it p star, is what the textbook uses, p with an asterisk, to represent the best point chosen, such that if you created rectangles out of these, the area lost is going to be equal to the area gained. And then you do the Riemann sum, and the limit is the partition tends towards 0, and you come up with the integral. So that's basically what's happening with the with our formula here for the area. Okay, so we have it as a theorem, and you can see that this is the area, the integral over the curve of the function with respect to s, where s is the arc length. And you might recall from Calculus 2 that the arc length formula is given by the square root of the, really coming from the distance formula, the change in x squared plus the change in y squared, the square root of that. So that times the function. So that times the differential dt represents the arc length. Okay, and that's the ds. So here's an example, and what we'll need to do to be able to use this formula is obviously calculate dx dt and dy dt. And here's our function, x cubed plus y, so that's the function of x and y that are both functions of t. But what we're going to have to do is substitute to be explicitly in terms of t, because t is the independent variable that we're integrating with respect to. So it looks like we need dx dt, so dx dt is just derivative of 3t, which is 3, and dy dt is the derivative of y, which is 3t squared. Okay, so now we could set this up for using our formula. So I'll just substitute, I won't rewrite the formula. And we'll have the integral from 0 to 1. Those are the limits of integration for t. Okay, and then we need x and y replaced by t. So x is 3t, but that has to be cubed, and then plus y is t cubed. And then we've got the square root of dx dt is 3, but that has to be squared. And then plus dy dt, which is 3t squared, but that has to be squared as well, and that's all with respect to t. Alright, so let's simplify this algebraically. Alright, this becomes 27 t cubed plus 1t cubed would give us 28t cubed. And then under the square root, we have 3 squared is 9, and then plus 3t squared squared, 3 squared is 9, t squared squared is t to the 4th. And that's with respect to t. Okay, so in terms of trying to integrate this, well, we see a radical, which is a power, so u to the n should come to mind. To make this simpler, though, let's factor out the 28, and at the same time, this 9 is common. So we could figure out, just doing this aside, 28 times the square root of 9, which is 28 times 3, or 84. So I could bring out the 84 out in front of the integral from 0 to 1 of, then I would have the t cubed, and left under the radical after I factor out the square root of 9 would be 1 plus t to the 4th, but that of course under the radical is the 1/2 power, and then that's with respect to t. Okay, so now I think we could see that a u substitution is going to work. We'll take our u to be 1 plus t to the 4th, the du 4t cubed dt, so 1/4 du is t cubed dt, and making the change of variables, here's u to the 1/2, the t cubed dt that's left over matches 1/4 du, so we'd have the 84 times the 1/4, and I'm just going to use dummy letters here. I'll say a to b of u to the 1/2 with respect to u. So that gives 4 goes into 84 21 times, and then we have integrating u to the 1/2, that's u to the 3/2 over 3/2. Evaluated, this would be again from a to b. Okay, and then that would be 21 times, so this is again off to the side, 21 times reciprocal of 3/2 is 2/3, and then 3 goes into 21 7 times, 2 is 14, so that'd be 14, and then let's put back our u was 1 plus t to the 4th, evaluated. Now we could say we're going from 0 to 1. And so now by the fundamental theorem of calculus, upper limit goes in. So we have 14 times 1 plus 1 to the 4th to the 3/2, and then minus lower limit goes in, so 14 times 1 plus 0 to the 4th raised to the 3/2. So I think the best we could do is just leave it 14 times 2 to the 3/2, because that's irrational, and then minus 14 times 1 is just 14. Okay, so that's how we evaluate the integrals, and although we use this generative procedure that they have at the bottom actually already, I kind of listed it because here's the notation that we use for a double. It's not really a double. It's not a double integral, but it's the integral of two pieces. One piece with respect to x, and another piece with respect to y. Now, for some reason, they don't put. I would think that maybe parentheses, but I guess they don't want to put parentheses because of the fact that you've got the differential separated. So it's just a notation that's used to indicate that it's really the integral of both pieces. So as you can see here, it's the integral of f of xy with respect to x, and then plus the integral of g of xy with respect to y. So that's just a notation that you got to get used to, meaning that you can integrate both pieces. But just as we did in the previous example, we're going to have to calculate, and this is just a general procedure. We might have to do different things depending on the nature of how the functions are given. But if x and y are both given as functions of t, as we had in this last example, we're going to calculate the differential dx and the differential dy, and then make our substitutions for x, y, dx, and dy, just as we did in this step here, and also use the limits of integration, and then we just integrate. So it's almost intuitively obvious, but just thought I might state some general procedure there. And so we have an example of such a thing, and you can see that it's using that notation that's indicating the two pieces. And so we want to evaluate that integral composed of these two pieces. So you get one part with respect to x, one part with respect to y, and here's the curve and the interval. So in terms of the formula, maybe we'll restate the main formula again, and it is that it's equal to the integral from a to b oh, actually, I'm sorry, this is a different situation. So we're not using, for this piece, the ds is part of the way this is separated as two integrals, so I apologize for that. So then that's when we use the general procedure I just suggested, which is to calculate dx dt. Okay, so derivative cosine minus sine, same argument t. You should think derivative of the argument, but that's not necessary because that's just simply 1. We need dy dt as well. So the derivative of sine, which is cosine, same argument. Again, you should think derivative of the argument, but in this case it's just 1 again. And so I suppose we should have gone to differential form right away. That would have been more convenient rather than having to write 2 steps. So I apologize for that. Okay, so we'll go to differential form right away. So dx would be minus sine of t dt, and dy will be cosine of t times dt. Okay, so that's more expedient, of course. Alright, so now we have everything we need to make our substitution. So it's going to be the integral in 2 pieces now. It's going to be the integral from 0 to pi over 2 of 2 times x and x is cosine of t, times y, which is sine of t, and then times the differential dx, which is minus sine of t. Here, let me do it. Times the differential dt. And then we have plus the integral from 0 to pi over 2. So the second piece of x squared, x is cosine t, so that's cosine squared t, plus y squared, y is sine of t, so that's sine squared t, and then times the differential dy, which is cosine of t, times the differential dt. Okay, so let's simplify this, and that is the integral from 0 to pi over 2. Actually, let's bring the negative and the 2 out in front. So we'll have negative 2, and then that's cosine of t times sine squared of t with respect to t, and then plus the integral from 0 to pi over 2 of, this simplifies neatly because cosine squared plus sine squared is 1, so we just get cosine of t dt. And what you might want to do, it's your choice, but I think what I'm going to do is separate these into two, or do the integrals separately. That is, off to the side, I'm going to say part 1 is negative 2 integral 0 to pi over 2 times cosine t sine squared t dt. Because this is going to require u substitution to get an odd power of cosine here. But it's just a basic u substitution, really. Calc 1 integral. Choose u as sine of t. Du is identically cosine of t dt. So this becomes negative 2 integral 0 to, should say, since I'm making my change of variables, here's my u squared, and cosine t dt identically makes up du. So I guess I should just say from a to b of u squared du. So that'd be negative 2/3. U squared integrates to be u cubed over 3, evaluated from a to b. So that's negative 2/3. Put back our u with sine. So sine cubed now of t, evaluated from 0 to pi over 2. So that becomes minus 2/3 sine of pi over 2 quantity cubed, and then minus a minus 2/3 sine of 0 quantity cubed. And the sine of pi over 2 is 1, so it's minus 2/3 times 1 cubed minus, or let's say plus 2/3, but the sine of 0 is 0, and 1 cubed is 1 times negative 2/3 is negative 2/3. So that's part 1. So I don't know if you wanted to say this is part 1 plus part 2, and then I'll do part 2 separately. Integral from 0 to pi over 2 of cosine of t dt. And so that's, cosine integrates to be positive sine, so sine of t 0 to pi over 2 would be sine of pi over 2 minus sine of 0, and that sine of pi over 2 is 1 minus sine of 0, 0, which is 1. So then we've got part 1 plus part 2 is equal to the negative 2/3 plus 1, which gives us 1/3. Okay, so you could do your calculus. Oh, I'm so sorry. Give me a second to look at that. Maybe I'll have to stop the video, but I got so excited I was writing all that down without having you look at it. Okay, but it's your choice if you want to do, if you come up with two integrals that may be a little tricky, and you want to do them separately, then by all means, like I did there, do so. Or if you want to do them within the context of a single, consideration, then that would be fine as well. Okay, so we'll stop right there and we'll come back and we'll finish off with a second example and then an application of the line integral as work.